Okay, let's
I want
start.
you to imagine, just for a second, that the universe isn't simply a random collection of stars and planets and swirling gas clouds.
Right.
What if instead reality is a colossal self-reading text? And what if the invisible stuff that makes up the vast majority of our universe, the stuff we call dark matter, is actually the cosmos's physical hard drive?
It's a massive concept. It fundamentally reframes how we perceive the night sky. I mean, you aren't just looking at an empty void dotted with photons from distant fusion reactions. You are looking at the architecture of an invisible, actively evolving memory network.
Exactly. So today's mission is to unpack an incredibly dense, genuinely fascinating stack of theoretical physics, cosmology, and information theory. We are exploring the boundary-pushing idea that information is not an abstract concept. It is a fundamental physical property of the universe.
Yeah, we're really getting into the weeds today.
We are. We're going to investigate the highly debated hypothesis that we might be living in a simulation, and then we're going to pull back the curtain on extra dimensions.
To set the stage for you, the material we're drawing from today is a wide spectrum. We have highly provocative, recently debated papers, like those published in AIP Advances, sitting right alongside firmly established standard cosmological frameworks, like the Lambda CDM model.
Right, the gold standard of cosmology.
Exactly. Our goal in this deep dive is to carefully separate the purely philosophical speculation from the rigorous mathematically backed facts. We want to see how matter, energy, and information might actually just be different faces of the exact same higher dimensional geometry.
The reason this matters to you is that if these frameworks hold up, it completely rewrites the fundamental rules of reality. You won't just look at the world around you as just stuff. You'll see it as a profoundly interconnected, active network.
Absolutely.
So let's jump straight into a specific paper that threw a massive wrench into the gears of traditional physics. We're looking at the work of Dr. Melvin Vopson, specifically his proposal of a second law of infodynamics, which was published in AIP Advances.
The disruption here stems from how we traditionally view entropy.
Right, the good old second law of thermodynamics.
Yeah, which dictates that physical entropy, the measure of disorder or the number of microscopic configurations that correspond to a macroscopic state in a closed system, it always increases over time. The universe marches toward a state of maximum thermodynamic equilibrium. Disorder grows. That's a foundational pillar of physics.
But Vopson is arguing something entirely different when it comes to information.
Yes.
He proposes that information entropy, which is the measure of disorder specifically within data states, can actually decrease over time. He's saying that information naturally optimizes itself, naturally compressing and finding the most efficient state.
Which is a huge claim.
It really is. And he extends this far beyond computer science. He's applying it to atomic physics, cosmological scales, and even biology. For example, the sources outline how he points to the genetic mutations of the SARS-CoV-2 virus, claiming those mutations weren't just random evolutionary chance, but rather a process of information optimization.
That is an incredibly bold leap.
Yeah.
He concludes that because we see this kind of data compression and optimization happening in nature, it perfectly mirrors computational processes. Therefore, he suggests, we are likely living in a simulation.
Wow.
He even formulates the force of gravity through the lens of information entropy, which strongly echoes the theories of entropic gravity proposed by physicists like Eric Verlinde. Vopson is essentially using a mass-energy information equivalence. He's treating information as a fundamental physical property, just like mass or energy.
But I noticed in the material, there is massive pushback from the broader scientific community regarding this specific conclusion. It seems like the internet grabbed the whole "we live in a simulation" headline and just ran with it, but the actual physics community threw up a lot of red flags.
Oh, absolutely. The analytical lens we have applied to Vopson's equations needs to be incredibly strict here. His mathematics regarding mass energy information equivalence might be internally consistent within his specific proposed framework. However, the scientific community is highly critical because information entropy, often thought of in terms of Shannon entropy, is absolutely not interchangeable with thermodynamic entropy in all contexts.
Right, the context is everything. Information entropy can decrease locally without violating any overarching laws of the universe.
Think about a crystal forming from a supersaturated solution, or a data compression algorithm running on a processor. These are examples of local decreases in information entropy, order arising from chaos. but they only happen by expending energy and increasing the overall thermodynamic entropy of the larger closed system.
The heat radiated by your processor while it compresses a file adds more disorder to the universe than the order created by the compression.
Exactly. It doesn't require a brand new law of physics to explain why a local system becomes highly ordered. The existing laws handle that perfectly well, provided you look at the whole system.
And when it comes to the biological claims, the pushback is even more severe. The analysis of SARS-CoV-2 mutations as purely data optimization is viewed as highly speculative and completely lacks backing in serious bioinformatics. You can't just point to a virus mutating into a more transmissible variant and claim the universe's computer is optimizing its code for efficiency.
Right. Viral mutation is driven by incredibly complex, tangible, selective pressures. We're talking about immune evasion, AE2 receptor binding affinity, and transmission bottlenecks in the host population. It is a messy biological reality driven by natural selection, not just clean data optimization seeking the lowest possible byte count.
Which brings us back to the simulation theory itself. Just because a system behaves like a computer does not mean it is a computer.
This is a crucial logical distinction that often gets lost in theoretical physics communication.
Let's use the fluid dynamics analogy from our notes to ground this, because I think it makes it so clear. Think about water flowing down a mountain stream. If you analyze the movement of the water, the eddies, the currents, the way it flows around rocks, it perfectly follows the incredibly complex Navier-Stokes equation.
Down to the microscopic level.
Right. So the water is effectively computing these equations flawlessly in real time. But nobody looks at a river and says, wow, water is a computer running a fluid dynamic simulation. It's simply water behaving according to the fundamental laws of physics.
That's a perfect way to look at it. If the universe is not a digital simulation running on some advanced alien civilization's hardware, we have to ask what it is actually doing with all this information. If we strip away the simulation philosophy and focus purely on the physics, a much more robust extrapolation is that the universe is a self-consistent system constantly trying to minimize contradictions.
Let's explore that idea of minimizing contradictions. What does that actually look like?
We can frame it as physical resonance. The universe operates on a physical level, particles, fields, energy, and an informational level, which comprises the states those particles can occupy and the mathematical correlations between them. The universe naturally favors stability.
Okay.
Unstable informational configurations, meaning states that require too much energy to maintain or that conflict with the surrounding environment, they decay rapidly. Stable configurations, on the other hand, survive and persist. It's not computer code optimizing itself to save RAM. It is physical resonance. The system is simply settling into the most stable, least contradictory state it can exist in.
I want to introduce the vitamin analogy here.
Yeah.
Because visualizing information as a physical entity is deeply counterintuitive.
It really is. It breaks your brain a little bit.
Information isn't matter. You can't hold a handful of it. And it isn't energy in the traditional work-performing sense. It acts more like a vitamin in a biological system. A vitamin is not the fundamental building block of your muscles, nor is it the primary fuel you burn for energy. But without that trace element, the complex metabolic pathways fail, and the entire biological structure collapses. Information works the exact same way. It provides the required structure, the necessary mathematical relationships for physical reality to function and maintain coherence.
And there is hardcore established physics backing this up, specifically Landauer's principle. Roelof Landauer demonstrated that erasing just one single bit of information, irreversibly changing a 1 or a 0 into a blank state, costs a minimum, unavoidable amount of physical energy.
It's a physical cost.
Yes. The equation dictates that this minimum energy equals Boltzmann's constant times the absolute temperature of the system times the natural logarithm of 2.
So the simple act of erasing data literally generates heat. It forces a physical thermodynamic consequence.
Exactly. Now, apply mass energy equivalence to that. Because information costs energy to erase, and energy is equivalent to mass, information inherently has a mass equivalent. It is infinitesimally small, but it is fundamentally non-zero.
The vital nuance here, though, and we have to be clear on this, is that the information itself doesn't weigh anything in isolation. It's the physical structure holding the information that carries the mass.
Right. The concept of mass as we traditionally measure it is essentially inertia in physical space, the resistance of an object to acceleration. Information, conversely, acts like inertia in state space.
State space. Okay, break that down for me.
It is the resistance a system has to changing its internal configuration. While information isn't a discrete particle you can isolate on a scale, the physical structure required to maintain that information, to keep those discrete states distinct and protected from thermal noise, absolutely carries a gravitational footprint.
Okay, let's unpack this. If information has this state-space inertia and a physical weight, however tiny, it absolutely requires a stable physical medium to be stored and preserved over cosmological timescales.
Because if it's constantly being scrambled, it's not memory.
Exactly. We're talking about an unfathomable amount of relational data here, where in the cosmos is the universe storing its memory. This leads us directly into one of the greatest anomalies in modern science, which is dark matter. We have to explore the hypothesis that dark matter actually serves as the cosmic hard drive.
To rigorously evaluate this, we really need to strip away the pop science mystique of dark matter and look at its observed physical properties. Standard cosmology relies on it to make up roughly 85% of all the matter in the universe. It exerts a massive gravitational influence, providing the scaffolding that holds galactic clusters together.
But it's totally invisible.
Crucially, yes, it does not interact with the electromagnetic force. It doesn't emit, absorb, or reflect photons. It interacts incredibly weakly, if at all, with the baryonic matter that makes planets, stars, and us.
When you lay the known physical properties of dark matter side by side with the strict physical requirements of what constitutes memory, the overlap is striking.
We have to rigorously define memory in a physical context here. We aren't discussing semantic meaning, human knowledge, or a digital recording. Physical memory is strictly defined as the ability of a system to preserve state differences over time with absolute minimal interference or decoherence from the surrounding environment.
So as to be isolated.
Highly isolated. A magnetic hard drive functions because its magnetic require a specific threshold of energy to flip. They don't easily change state on their own just due to ambient room temperature.
Because if a storage medium is constantly reacting to it, you'd suffer catastrophic data loss instantly.
It would be chaos.
That makes the absolute darkness of dark matter its most vital feature. If dark matter interacted with light, heat, or electromagnetism, its internal states would be constantly bombarded and reset by the cosmic microwave background and stellar radiation. Its total isolation from the electromagnetic spectrum is the exact physical property required for a perfect, long-term, non-volatile storage medium.
This naturally leads to the question of encoding. How is the information actually stored in this dark medium? It is highly unlikely to resemble binary code. The physics suggests it would be stored in topological defects of the vacuum or in the internal hidden degrees of freedom of the dark matter particles themselves.
What kind of hidden degrees of freedom?
Perhaps specific quantum spins or phases that our electromagnetic instruments are fundamentally blind to. Furthermore, this wouldn't be localized memory like a single file on a sector of a disk. It would consist of vast distributed correlations across light years, functioning more like a holographic memory where information is encoded in the relationships and interference patterns of the entire macroscopic structure.
Which provides a fascinating lens through which to view the large-scale structure of the observable universe. When you look at the distribution of galaxies, they don't sit randomly in an isotropic void. They perfectly trace the underlying invisible web of dark matter. The glowing baryonic matter clusters intensely at the nodes and stretches along the vast filaments. It raises a provocative question. Is regular glowing matter simply reading the structural template that was pre-recorded and stored in the dark matter web?
We need to look at the evolution of the cosmic web to really understand this. As the universe expands, this web grows hierarchically through gravitational instability. Slight overdensities in the early universe collapse into flat structures we call Zeldovich pancakes, which then funnel matter into long, intersecting filaments.
Where those cross.
Where they cross, you get massive, dense nodes, superclusters, and they leave behind vast, empty voids. The structure isn't evolving with a biological, teleological goal. It is crystallizing based purely on the physics of.
But the massive superclusters, the structures that span hundreds of millions of light years and take billions of years to coalesce, represent the universe's long-term memory. They are the deepest, most resilient structural correlations of reality.
The riverbed analogy is the most accurate way to visualize this dynamic.
Let's hear it.
The dark matter web isn't actively writing a script or a line of code dictating the exact coordinates of a specific galaxy. Instead, it codes possibilities and constraints. A physical riverbed doesn't hold the water tightly in place. It dictates the path of least resistance. It establishes the topological boundaries of where the water is physically permitted to flow.
So the dark matter web is the gravitational riverbed of the cosmos.
Precisely. The glowing galaxies, the stars, the interstellar gas, that is the water flowing through the paths of possibility laid down by the underlying structural memory.
The visual similarities across different domains of nature are impossible to ignore here. A map of the cosmic web placed next to an image of a biological neural network, or the root system of a complex plant, or even the foraging patterns of a slime mold, they look practically identical.
The branching is unmistakable.
They share that same interconnected branching morphology, but it isn't some mystical coincidence. They look the same because they are all physical systems rigorously constrained by the exact same mathematical geometry of optimal transport and energy minimization. They are structures mathematically compelled to distribute resources, mass, and information as efficiently as possible across a spatial volume.
So we have this massive, intricate, invisible memory web dictating the flow of reality. But this confronts us with one of the most stubborn paradoxes in modern astrophysics.
The invisible elephant in the room.
Right. If dark matter is this massive, heavy scaffolding taking up 85% of the universe's mass budget, why haven't we detected a single particle of it in our most sensitive underground vats of liquid xenon? And why does it behave so anomalously, particularly in the most extreme gravitational environments?
This brings us to the cutting edge of theoretical physics, the higher dimensional shadow. The dimensional slice hypothesis offers a seemingly elegant solution to the paradox of dark matter's invisibility. What if dark matter isn't an exotic, magical, weakly interacting massive particle, a WIMP, that refuses to trigger our detectors? What if it's totally invisible to us simply because it exists in high...
Might merely be its 3D projection. It is a shadow of a higher dimensional structure intercepting with our three-dimensional slice of reality.
How does that even work mathematically?
The fundamental reason this works mathematically relies on the distinct ways different fundamental forces propagate. According to general relativity, gravity isn't a traditional particle zooming through space. Gravity is the literal shape, the curvature of space-time geometry itself. Because it is a property of the space, gravity can leak across all dimensions.
Okay, so gravity is essentially dimension agnostic.
Exactly. But the standard model forces, specifically electromagnetism, the light and heat that allow us to interact with the universe, they are mathematically confined to our specific 3D slice, which string theorists call our brain.
So gravity bleeds through the dimensional boundaries, but light is permanently tethered to the brain. The conceptual math behind this is fascinating.
If you look at gravitational force in a traditional 3D universe, it follows the inverse square law, weakening over distance. But if you introduce extra compactified dimensions, the gravitational force spreads out differently at specific scales. The mathematical formulation demonstrates that force becomes proportional to 1 over r to the power of 2 plus n, where n is the number of extra dimensions.
That changes everything about how gravity behaves on a massive scale.
Yes. Consequently, an object that is incredibly dense and localized in a 4th or 5th dimension projects its gravitational influence into a 3D world. But because that curvature is spread across a higher geometry, what we measure in 3D feels like a massive but highly diffuse, ghost-like gravitational web.
This higher dimensional projection model elegantly solves a massive headache for astrophysicists known as the core cusp problem. To give some necessary context for you listening, when cosmologists run massive n-body supercomputer simulations of how standard cold dark matter particles should behave under their own gravity, the mathematics dictate they should clump together into incredibly sharp, infinitely dense spikes at the very center of galaxies.
Which is known as the Navarro-Frank-White or NFW profile. They predict a sharp cusp.
Density core of dark matter.
Traditional particle physics has struggled for decades to explain that flattening without inventing overly complex feedback loops from supernovae. But higher dimensional geometry resolves it effortlessly. It also resolves the complete lack of dark matter black holes.
This is a huge point.
If dark matter is just regular, heavy particulate matter, why hasn't it collapsed into black holes everywhere in the early universe? To form a black hole, you must compress a massive amount of matter tightly enough within a 3D spatial volume to overcome degeneracy pressure and close an event horizon.
To squeeze it past its Schwarzschild radius into a singularity.
But if the mass you are attempting to squeeze actually possesses depth in a 4th or 5th dimension, you physically cannot compress it all into a 3D point. As you apply compressional force in our three dimensions, mass simply shifts or leaks further into the higher dimensions. You can never achieve the localized 3D density required to form an event horizon in our specific brain.
I love the shadow analogy from the sources for this. Imagine you are a 2D being living on a flat wall. A 3D sphere is casting a flat 2D circular shadow onto your world. If you, constrained entirely to your 2D geometry, try to crush that shadow to compress it into a tiny singularity on the wall, you will inevitably fail.
You're just crushing empty space.
Exactly. No matter how hard you squeeze the 2D footprint, you are never actually crushing the 3D sphere that is casting it. The mass of the sphere is safely distributed along an axis you cannot access or manipulate. That is precisely why higher dimensional dark matter will never undergo total gravitational collapse into a singularity in our universe.
The logical conclusion drawn from this is that the gravitational centers of galaxies might not harbor classic, infinitely dense, singular black holes. Instead, they could be dense, extended, flattened cores of dark matter.
Fermionic DM cores.
The literature often refers to these as fermionic DM cores. They act as a 3D projection of a higher dimensional mass concentration. And this isn't just whiteboard mathematics. This is an actively observable hypothesis. Astrophysicists are currently utilizing ultra-precise. They're searching for minute orbital deviations. Wobbles that would mathematically prove those stars are orbiting a diffuse, extended, higher dimensional core rather than a pinpoint singularity.
That is incredible. The implications of this higher dimensional geometry extend even further, offering a framework to explain one of the most notoriously confusing phenomena in quantum mechanics, which is quantum entanglement. Einstein famously derided it as spooky action at a distance, where two particles interact instantaneously, regardless of the spatial distance separating them. It seemingly violates the universal speed limit of light, but the higher dimensional model offers a beautifully simple geometric perspective.
If you have two entangled particles separated by 1,000,000 light years in our 3D space, standard physics wrestles with the idea of two discrete objects communicating infinitely fast. However, if you elevate your perspective to a higher dimension, they might not be two separate objects at all. They might literally be the exact same single connected geometric object.
So when a scientist measures the spin of one particle on Earth, and the entangled particle in the Andromeda galaxy instantly assumes the opposite spin, it is not a signal traveling faster than light across the void.
There is no signal crossing the gap. It is simply the observer viewing the full geometric object from our incredibly limited 3D perspective. Consider a U-shaped pipe dipping into a 2D plane of water. The 2D beings living on the surface of the water see two distinct, unconnected circles. If you, in the 3D space, wiggle the pipe, both circles move instantaneously.
And the 2D beings perceive it as magic, faster than light communication between two separate entities.
Exactly. But from the 3D perspective, it's obviously just one continuous physical object. Quantum entanglement could simply be the manifestation of a higher dimensional structure intercepting our 3D brain in multiple locations simultaneously. Non-locality is an artifact of a low-dimensional perspective.
Here is where it gets really interesting. If there is one extra dimension responsible for the universe's other terrifying mystery, I'm talking about dark energy, the repulsive force that is actively accelerating the expansion of the universe. This brings us to the concept of the fractal matryoshka of reality.
We are shifting into the absolute vanguard of theoretical cosmology here. The frameworks currently being debated by physicists frame the universe as a multi-layered hierarchical structure, like Russian matryoshka dolls nested inside one another.
Let's clearly define these nested levels. Level 0 is our everyday experience. It's our 3D reality, our brain, where the standard model of particle physics operates, where normal matter, light, and humans exist. Stepping out one layer brings us to level 1, which the theoretical models refer to as bulk 1.
Right.
This is an extra dimension, or a specific set of dimensions, whose geometric curvature generates the localized gravitational effects we identify as dark matter. Stepping out even further brings us to level 2, or bulk 2. This is an even higher dimensional space whose overall geometry generates the macroscopic, universe-expanding repulsive effects of dark energy.
We must ground this in the rigorous scientific literature, though. We are looking at specific mathematically detailed models. For instance, the Germahanta and Schrock model. This framework proposes an extra-dimensional space where particles are tightly localized within our 3D reality, but their quantum mechanical waveforms are permitted to propagate into an extra dimension.
Just the waveforms.
Yes. This specific propagation perfectly accounts for the missing mass we attribute to dark matter, entirely eliminating the need to invent exotic, weakly interacting particles.
The dark dimension framework is also particularly compelling because it intersects with string theory, specifically relying on what physicists call the swampland criteria.
The swampland concept is vital to understand. All mathematically possible universes can actually exist consistently with quantum gravity. The swampland refers to the massive set of theories that look fine at low energies but break down entirely when you introduce quantum gravity.
So they are mathematically impossible in a real universe.
Correct. By applying strict criteria to avoid the swampland, the dark dimension framework predicts the necessary existence of one relatively large extra dimension. And by large, in quantum terms, they mean roughly the size of a micron.
A micron is absolutely massive compared to the Planck length, and this specific micron-sized dimension generates what are known as Kaluza-Klein gravitons.
Kaluza-Klein, or KK compactification, is a foundational concept in extra-dimensional physics. If a dimension is curled up into a tiny circle, a particle or a field moving through it acts like a wave resonating inside a closed tube. It sets up standing waves. This higher dimensional resonance manifests in our 3D world not as movement, but as extra mass.
This is where the math lines up so beautifully.
It does. The dark dimension framework calculates that the KK gravitons resonating in this micron-sized dimension would possess a mass of roughly 1 to 100 kilo electron volts. What is astonishing is that a particle with that exact mass profile behaves perfectly, mathematically, as the cold dark matter we observe structurally in the universe.
We also need to examine brain world models, specifically the DGP model, named for Diwali, Gabadadze, and Porati. In these models, our entire 3D universe is a membrane floating in a multidimensional bulk. This fundamentally modifies how gravity functions on massive cosmic scales. At short distances, gravity behaves normally.
Speeds of galaxies, and the accelerated expansion of the universe strictly through the geometry of the brain interacting with the bulk without needing to invent a single new dark matter particle.
The true explanatory power of this fractal Matryoshka model, the nesting of bulk 1 and bulk 2, is how it directly attacks the cosmic coincidence problem. This is a major philosophical and physical headache in standard cosmology. Right now, in this exact epoch of the universe's 13.8 billion year history, the energy density of dark matter and the energy density of dark energy are roughly within the same order of magnitude, about 27% to 68%.
It's a highly suspicious ratio.
Why? If dark energy is a constant that dominates more as space expands, and dark matter is diluting as volume increases, why are we lucky enough to exist in the incredibly narrow window of time where they are comparable?
Standard cosmology often shrugs and relies on anthropic arguments or labels it a lucky coincidence. But the extra-dimensional models eliminate the need for luck entirely.
How so?
In the fractal Matryoshka framework, the ratio of dark matter to dark energy isn't an accident of timing. It is strictly dictated by the geometric hierarchy of bulk 1 relative to bulk 2. The topology of the higher dimensions requires this specific energy distribution to remain stable. Crucially, this implies that dark energy evolves over time as the higher dimensional geometry shifts.
This is where theory collides with groundbreaking observation. Recent data from the DSI mission, the Dark Energy Spectroscopic Instrument, has sent shockwaves through the physics community. By mapping millions of galaxies and quasars to measure baryon acoustic oscillations, the DSI data actively hints that the strength of dark energy might be weakening over time.
This is a huge deal.
If dark energy is dynamic and weakening, it fundamentally breaks the standard lambda CDM model of a constant lambda. It heavily supports these dynamic extra-dimensional Matryoshka models, where the equation of state is allowed to fluctuate based on bulk geometry.
It is a phenomenal time to be an observational cosmologist. But inevitably, dealing with 4, 5, or 10 dimensions raises a question that borders on the anthropic. Why do we only experience 3 spatial dimensions? Why are we confined to the 3D brain?
Right, if there are 10 dimensions, what are the other 7?
The literature, particularly within string theory, addresses this through mechanisms like the Brandenburger-Vafa mechanism. The physics suggests that in the unimaginably hot, dense, chaotic state of the Earth act and annihilate each other. The topological mathematics demonstrates that this unwinding process is only highly probable for 3 spatial dimensions.
So 3 is the magic topological number.
Therefore, only 3 dimensions could stably inflate to macroscopic size, while the rest remain permanently tightly wound up at the quantum level.
The DNA, a massive, unfathomably long string of biological code, is tightly coiled and compacted inside a microscopic cell nucleus. It does this to save spatial volume, yet it holds the entire architectural blueprint required to construct a fully functioning human body.
That precisely mirrors how compactified dimensions function. They are coiled up at the micro level, perhaps a micron across, as the dark dimension framework suggests, holding the structural blueprint of the cosmos. Their specific geometry dictates the flow of gravity, the distribution of macroscopic mass, the rules of quantum entanglement, and the dynamic ratio of dark energy. They hold the structural blueprint of the entire cosmos without occupying macroscopic 3D space.
Let's bring this all the way back from the micron scale of Kaluza-Klein gravitons and the macro scale of the cosmic web, right back to the everyday experience of reality. So what does this all mean for you?
To synthesize the immense ground we've covered today, we are highly unlikely to be discrete lines of code trapped inside a digital computer simulation optimizing itself to save RAM. The physics simply doesn't require that leap. Instead, the data suggests we live in a remarkably self-consistent physical informational universe. Dark matter is not just a missing, wickedly interacting particle. It serves as a stable, deeply isolated, extra-dimensional hard drive. It physically holds the vast correlations, the structural possibilities, and the memory of the cosmos.
And our entire 3D reality, everything we can observe, touch, build, and destroy, is just one single slice. It is the visible surface of a fractal, higher dimensional structure.
This isn't abstract late-night theorizing either. This is the absolute frontier of modern empirical science, actively being tested right now. When observatories like DSI map the dynamic, changing nature of dark energy, or when the GAIA satellite tracks the microscopic astrometric wobble of a star near the galactic core, searching for extended fermionic cores, science is actively hunting for the geometry of the invisible. We are looking for the precise gravitational shadows cast by higher dimensions.
I want to leave you with a final thought to ponder, one that builds on this idea of the universe as a vast memory web of structural possibilities. If the macroscopic structure of the universe is governed by an underlying higher dimensional memory web that purely dictates the flow of physical possibilities, when you make a choice today, are you simply creating a new biological pathway in your brain, or are you physically carving a microscopic new filament into the geometric shadow of the cosmos itself? Keep diving, and we'll see you next time.